fabrication, and this fused filament fabrication for short, or AKA, is 3D printing. So it started as a method to create small parts, then slowly and gradually it became the most widely adopted additive manufacturing technique. And then it also shifted to our industry, and we can see it in concrete and clay printing. We noticed that despite the importance of this fused filament fabrication, there is still something missing, which is a general approach for automated defect detection, regardless of the shape of the printed product, as well as the defect class. So this is why we thought, okay, maybe we should do something. And this is why we did automated defect detection, ADD for short, in fused filament fabrication processes. And then, since we're speaking about us as civil engineers, we wanted later to translate it into clay and concrete printing. So fused filament fabrication defects, we have 3D printers, and those 3D printers might have errors, and those errors translate into defects. And the defects consist of irregularities, unwanted irregularities, and structural failure that might degrade the quality of the printed product. And those might appear on the, might be visible on the surface of the printed product, or might be internal. And they result in a time and material being wasted, because most of the time you have to restart the whole printing process. And also it requires continuous human supervision. So for those defects, specifically for 3D printers, we have stringing, for example, we have cracking, we have blobs, we have spaghetti, and under extrusion, and layer gaps. So for our approach, it consists of two phases, as everybody else here that presented. So first, we prepare the data, and second, we create or develop the classification model. So you start with collecting the data, you do data pre-processing, and then later you do data augmentation if you need, and splitting. Then you define which model you want to use, you train the model, you check the accuracy of the model, and then finally you have your classification model. So for our implementation, we collected data set, more or less a bit more than 4,000 images. Those we have collected ourselves or took from online sources for products or 3D printed products that has defects and also defect-free. Then we pre-process this data. Since they come from different sources, they come with different sizes. Also, we change them into a grayscale image to not connect specific type of defect with a specific color, and adjusted the viewing angle if needed, and then labeled them. Then we used data augmentation techniques such as mirroring, light exposure to increase the size of this data set to 12,000 images. Then we split this data. So we designed a small graphical user interface that helped us make the process a little bit faster. Then we, again, used a convolutional neural network. Specifically, we went into the direction, as our colleague here spoke, the YOLO, which is called You Only Look Once. And this YOLO is considered the state-of-the-art architecture for detecting and tracking objects, instance segmentation, image classification, and so on. So for convolutional neural network, we all, I guess, know what is it. So you have an input layer, you put your image, it sends it to the convolutional layer or kernels that create feature maps. Then those feature maps goes to the pooling layer. And yeah, I think you all know the story. Then it goes to the fully connected layer where it creates a classification score, and then the classification score goes to the output layer where it tells you which category it is or class it is. So for our work, we looked at 4 different YOLO models. So we took the YOLO V8, V9, V10, and V10L, and V10B. And this is, for example, the training process from the YOLO V8 and YOLO V9. We use, of course, the training and validation data for this. And then to evaluate the images or to evaluate the models, we use the testing data sets that was not, of course, introduced during the training. And then we chose the model that have had the best performance, which is the YOLO V9C. For the validation, we had designed 3D prints to mimic specific types of defects. And then this is, for example, here we have the setup of the experiment. So we have here a Raspberry Pi connected to a camera that takes images, and those images then get sent to a computer where you have the model. So this is an example from one of the printing processes. And as you can see the defects being detected. And we took it one step further. We also integrated another graphical user interface to manage the whole process and stop also the printing process at the end when the defect is there for more than 25 seconds. Another validation we have done, also using videos we took ourselves. Here are videos from different printing processes. And again, the model was performing pretty okay. So to summarize, as we spoke, this fused filament fabrication, as one of the most widely adopted additive manufacturing technique, is being increasingly used in our industry, such as concrete and clay printing. But despite the importance of it, a general approach for automated defect detection was still missing, and this is why we did the ADD approach, and we wanted to use it for clay printing. This is the clay printer in our lab, and yeah, we slowly translating it into this domain. Thank you.